Close your eyes for a moment if you can, and just imagine the sheer raw power of a major river. Not just some static line you see on a map, right? But a living, breathing, moving thing constantly carving out the land around it. Think of the Amazon. Just this immense force shaping its own reality. It's something we often take for granted. And that dynamic, that ever-changing nature of the world's largest rivers, that's exactly what we're diving into today. This deep dive is all about how these incredible systems dynamically shift and evolve. We're focusing on a specific type called anabranching structures in the upper Peruvian Amazon. Our mission, really, is to unpack the fascinating relationship between a river's main channel and its secondary channels, and how their sinuosity, basically, how curvy or straight they are, plays this crucial, often surprising role in shaping the landscape. To guide us through this, we're drawing heavily from a really insightful 2015 research article by Frias and colleagues, published in Water Resources Research. And this isn't just theory. It's a study that brings together decades of satellite imagery, incredibly detailed field measurements taken right on the river.
Yeah, boots on the ground, or maybe boots in the water.
Exactly. And sophisticated numerical modeling to reveal these often hidden river dynamics. It's a gold mine of information, really, and we're here to distill the most important nuggets for you.
So, okay, to really get into this, we first need to define what an anabranching river actually is. Imagine a river that's not just a single continuous stream. It's also different from a braided river, which is more like, a tangled web of many small temporary streams constantly shifting.
Right, much more chaotic looking usually.
Yeah, an anabranching river is more like a major highway system. You've got significant, long-lasting side roads that are themselves active routes. You have a main channel, which is typically wider, coexisting with several secondary channels that are narrower. And crucially, their roles aren't fixed. A main channel can actually become secondary over time, and vice versa. It's a pattern you see in many of the world's largest rivers, including, of course, the Amazon.
And the Peruvian Amazon, specifically, has this unique trait of switching between single and multi-channel patterns as you move along its length. It's like this vast, pulsating circulatory system for the landscape, always adapting.
And this study really highlights a critical point. To understand these rivers, you can't just look at their map shape, what we call their planform. It's not enough.
There's more going on underneath the surface, literally.
Exactly. You have to consider so much more. Things like the bed morphology, the detailed shape of the riverbed itself, the strength and makeup of the banks, the characteristics of the whole floodplain, and really importantly, the hydrodynamics, how the water actually flows, how it moves within the system.
And this research actually filled a really important gap, didn't it?
It did. While there were numerical models out there for, say, braided rivers and lots of field data on the Amazon focused on broad trends, there was a specific need to understand the interaction between these main and secondary channels within these anabranching structures.
Right, like having a map of the roads, but not knowing how the traffic actually flows between the main highway and the side streets.
Precisely. That's where this study really shines, giving us that missing piece.
Okay, so to tackle this huge task, the researchers picked two very specific study sites in the Peruvian Amazon. What were they like?
Right. So first, there was the MS site near Iquitos. This one's characterized by a medium to high sinuosity main channel, so pretty curvy.
Okay.
Then they looked at the LS site down at Tres Fronteras, right where Brazil, Colombia, and Peru meet. This site has a low sinuosity main channel, much straighter.
Big contrast.
A very big contrast. And a key detail they noted was that in both locations, at least one of those secondary channels sits right up against the edge of the geological valley. That turns out to be really crucial for how they behave.
And they looked back in time, right, using satellite data.
They did, and for a long time. To capture those big long-term changes, they tapped into an incredible resource. 30 years of Landsat satellite imagery for the MS site.
30 years.
And 29 years for the LS site. So we're not just looking at a few snapshots. It's like watching decades of time-lapse footage from space.
Wow. How do they process all that?
Well, they process these images to identify water versus land areas, then meticulously trace the riverbanks over all those years to understand how the channels shifted. And from that, they calculated key things like channel width, their sinuosity, that curveness measure, and, importantly, how fast the banks were migrating each year, the maximum rates.
But they didn't just stay in orbit, right? They got down on the ground or on the water?
Absolutely. They grounded that historical view with real boots-on-the-water work. They took detailed field measurements using things like echo sounders, basically sonar, to map the riverbed shape in 3D.
Okay.
and acoustic Doppler current profilers, ADCPs, to precisely measure water velocity at different depths. Very detailed stuff.
Uh-huh.
They even used GPS for super accurate water surface elevations.
And then they brought in the computers.
Yes, and this is where it gets really clever. They took all that detailed real-world data and fed it into a sophisticated two-dimensional numerical model.
Like a virtual river.
Exactly, like creating a virtual river on a computer. This let them simulate exactly how water flows at different river stages, low flow, high flow, in between. And critically, they checked this virtual river against their actual field data to make sure it was accurate. They calibrated it.
Right.
This combination, the long-term view from space, the on-the-ground measurements, and the computer modeling was absolutely essential for unlocking the full complex dynamics.
So, okay, with all these sophisticated tools, all this data, what did Frias and his team actually find? What were the big insights from these two very different river sections?
Well, this is really one of the study's most remarkable findings, how the sinuosity, the shape of the main channel, fundamentally dictates which parts of the system are the most active shapers of the landscape.
It dictates the main players, essentially.
You could put it that way, yeah. It's a subtle but incredibly powerful distinction.
And this is where the research really kind of flips our common understanding, isn't it?
Right.
Especially when we look at that MS site, the really curvy one. What they found there was, well, it wasn't the big main channel doing all the heavy lifting of reshaping the land. Get this. It was the secondary channels. Those often overlooked side roads, they were the dominant mechanism for reworking the floodplain. I mean, think about that for a second. The smaller channels driving the most change.
That's exactly right. They observed and, importantly, modeled much higher flow velocities in these secondary channels compared to the main channel. And this was true across all flow stages, low, transition, and high flows.
So faster water means more power to erode and move sediment.
Precisely. It implies higher bed shear stresses. That's the force the water exerts directly on the riverbed. Imagine water not just flowing over the bottom, but actively scrubbing and pushing it, leading to more erosion, more deposition, more change.
And these weren't just trickles either, these secondary channels.
Not at all. They carried a really significant portion of the total water flow, up to 23% during high flow conditions.
Wow, nearly a quarter of the whole river's discharge going through these seemingly smaller paths.
Yeah. And they saw clear examples of this in action. Secondary channel MSA2, for instance, was actively migrating sideways, laterally. So much so that it actually collided with another secondary channel, MSA3. And that collision ultimately led to the abandonment of a section of channel.
Nature rearranging the plumbing.
Exactly. And interestingly, that other channel, MSA3, it was constrained by the valley edge we mentioned earlier. That suppressed its sideways migration, showing how the local geology interacts with these powerful water dynamics.
Okay, so if the secondary channels at the MS site were so dominant, what was the main channel doing? Was it just sort of sitting there?
Oh no, the main channel MSA0 was certainly not static. It was migrating laterally, too, quite significantly, averaging up to 300 meters per year in place.
300 meters, that's huge.
Yeah, it is. And its sinuosity, its curveness, significantly increased over the study period, going from about 1.35 up to 1.64 over 28 years. And all this dynamic activity also led to the formation of new features, like new islands. They identified one, MSI6 forming because the channel widened and sandbars built up in the middle.
Now, let's pivot. Compare that to the LS site, the one with the low sinuosity, the straighter main channel. You said the story flips.
It really does. It's almost a reversal of roles.
Yeah.
Here at the LS site, the main channel planform dynamics are clearly the dominant force shaping the landscape.
So the main highway is doing most of the work here.
Precisely. At the LS site, the high water velocities were primarily concentrated in the main channel. The secondary channel showed much smaller velocities.
Okay, that makes sense intuitively.
Yeah, and it meant the secondary channels at LS carried a lower percentage of the total water flow, only up to about 13% during high flow, compared to the 23% at the MS site.
Why was that, did they figure out?
Well, the study attributed this partly to the smaller angles where these secondary channels branched off the main one. It was just harder for the water to divert into them efficiently.
Geometry matters.
Right. No.
But the main channel at LS was still active, right? It wasn't completely stable?
No, definitely still active. The main channel, LSA0, migrated laterally at an average of about 230 meters per year.
Still pretty impressive migration.
Absolutely. And its sinuosity did increase slightly, though much less dramatically than at MS, going from 1.04 to 1.09 over 29 years. They also saw a mid-channel bar developing in the main channel there, which eventually stabilized and became a new island, LSA-4.
And, you mentioned this LS site has a really direct human implication.
Yes, this is quite concerning. One of its secondary channels, LSA-2, is actually experiencing less and less water flow. Why? Because of bed accretion, basically. Sediment is building up on its bottom, making it shallower. And if this trend continues, it could lead to significant sedimentation problems in the harbor at Letitia, which relies on that channel. It could potentially prevent large vessels from using the facilities there.
Wow, so these natural river shifts have very real-world consequences for infrastructure and transport.
Absolutely. It's a stark reminder.
So let's connect the dots then. Why does the sinuosity make such a difference? Why does curvy versus straight dictate whether the main or secondary channels dominate?
Right. This is the core mechanical explanation they uncovered. In the high sinuosity MS site, the main channel is so curvy, the water essentially has to travel a much greater distance to get downstream compared to the straighter path offered by the secondary channels.
Okay.
This extra distance and the bends create more resistance, like a bottleneck in the main channel. This resistance allows, or almost forces, more water to divert into the secondary channels, which offer a slightly more direct route in places. That diversion results in the higher velocities and greater erosional impact we saw in those secondary channels at Amazon.
Huh. So it's almost counterintuitive. The main channel's curviness actually empowers the secondary one.
Exactly. It gives them a hydraulic advantage, you could say.
And meanwhile, at the low sinuosity LS site,
The opposite is true. The main channel is relatively straight. It's a more efficient path for the water, so the water discharges faster and more easily through it. Less water gets naturally diverted into those secondary channels because the main channel is just, well, faster.
like an express lane.
Pretty much. So the main channel acts like the superhighway for water, keeping most of the erosional action and the landscape change concentrated within itself.
That's fascinating. And they mentioned something about channel width not being the whole story.
Yes, an important caveat. The study found that while secondary channels are generally narrower, often less than 75% of the main channel's width, their width alone doesn't reliably predict how much water they actually carry.
So you can't just look at a map and say, narrow channel, less water.
Right, it's not representative of the actual discharge partition, how the flow is divided. Other factors, like that bifurcation angle we mentioned, where the channel branches off and the overall hydraulic setup, are more critical in determining how much water goes where.
Okay, good point.
Oh.
Overall in the region, which type is more common?
Interestingly, the research indicated that most of the anabranching structures in the upper Peruvian Amazon River actually have low sinuosity main channels, like the LS site.
So the main channel playing the dominant role is probably the more common scenario across that whole vast region.
That's what the evidence suggests, yes.
So after digging into all this incredible detail, what's the bottom line? What does this all mean for us trying to understand, maybe even live alongside these immense and powerful rivers?
Well, the core takeaway from this deep dive is, I think, incredibly clear. The sinuosity, just how curvy or straight a river's main channel is, acts as a key control. It determines whether that main channel or its secondary channels are the primary drivers of change in these really complex anabranching river systems.
It's not just about size, it's about shape dictating power.
Precisely. Shape dictates the hydraulics, which dictates the geomorphic work being done.
And the practical value here seems huge. This isn't just academic.
Not at all. The rigorous methods they use, that brilliant mix of long-term satellite views, detailed field measurements, and the sophisticated modeling, it's all reproducible. This work can serve as a vital baseline for future studies of the Peruvian Amazon and similar rivers elsewhere. It helps us build better tools to predict how these powerful rivers will continue to evolve.
And maybe anticipate where human activity might clash, or hopefully coexist, with their natural dynamism.
Exactly. Predicting river evolution is key for sustainable management.
Did the study point towards next steps? What's still unanswered?
It did. While they did a fantastic job characterizing how the water gets redistributed, the velocities and discharges, they pointed to a critical area for future research, understanding the redistribution of sediments.
Ah, the sand, silt, and clay being carried.
Yes, both the heavier stuff dragged along the bed load, and the lighter particles suspended in the water. How that material gets divided among the channels at different flow stages is still a big question. Understanding sediment transport will be absolutely key to fully grasping the long-term evolution and predicting issues like the potential sedimentation facing Letitia's harbor.
What an aha moment this deep dive offers, though. It really pulls back the curtain on the hidden forces at play in what looks like, just a chaotic, multi-channeled river system. You've just gained a real shortcut, hopefully, to being well-informed about the fascinating and incredibly powerful dynamics of these great rivers.
So, maybe a final thought to leave you with. Considering this continuous long-term dynamism we've discussed, this constant shifting and reshaping, and thinking about that specific example of potential sedimentation impacting Letitia's harbor, how might our human infrastructure, our development plans in these river environments need to adapt? How can we innovate to truly coexist with, rather than constantly fight against, the natural, powerful, and ever-changing forces of these large river systems, not just for next year, but over decades and even centuries? Something to mull over.